So for discrete time Markov chains, we could find the n-step transition probability, P of n, by looking at matrix power, P to the n. So in continuous time, we've set up these differential equations, the forwards and backwards equations. It turns out that they can be solved by something called a matrix exponential, which is when you sort of take e to the power of a matrix. And this is kind of the continuous time version of the matrix power p to the n that we had in discrete time. Now this only really applies when the state space is finite, because otherwise it's not really clear what matrix multiplication means exactly. But we're going to see how the forward and backward equation are solved using something called the matrix exponential. So let's start by defining that and reminding ourselves about the normal exponential function as well. So let's start with our old friend, the old-fashioned normal exponential, just the exponential of a number, x. So you should remember that the exponential of a number x, which we sometimes write as e to the x, or sometimes write as x of x to emphasize the fact it's a function. You should probably remember that it's defined by a Taylor series, which is the sum from n equals 0 to infinity of x to the n over n factorial. So to write out the first few terms, x to the 0 is 1, and then it's plus x squared over 2 factorial is 2, 3 factorial is 6, and so on. And so basically we can just use this definition as it exists, but bung a matrix in there. So if capital A is a square matrix, then e to the a, or if you prefer x of a, it's just going to be the same sum, n equals 0 to infinity, of matrix a to the n over n factorial. And of course we know what a matrix power a to the n is, so you know we can divide some of those by a number and add them all up, and that's all fine. So again, a to the 0, in the same way as that x to the 0 is 1, a to the 0 we interpret to be the identity matrix. It's a, then it's, half lots of a squared, plus a sixth lot of a cubed, and so on. So here a is a square matrix. It needs to be square in order for the multiplying it by itself to make sense. You can't multiply a non-square matrix by itself, the dimensions don't work. So that defines the matrix exponential. And so in the same way as that a computer can do p to the n really quickly, a computer can do e to the power of a matrix really quickly. There's some details on one of the problem sheets about how that's done using eigenvalue methods. We could note a few facts here. Obviously, a matrix, normally it matters which way round you multiply matrices, right? A times B is not always B times A. But of course, a to the n times a is equal to a times a to the n, because those are both a to the n plus 1. So that means that a matrix A and its exponential, it doesn't actually matter which way round you write them, because you bring it inside the sum and all those things are just a to a slightly different power. So it is true that a e to the a and e to the a are the same, even though multiplying matrices, normally the order matters, but here the order doesn't matter. That will be important in just a moment. So in the same way as we copied the definition for the normal exponential to get the matrix exponential, it turns out that many of the properties work in the same way. I'm not going to prove these, but you can check them if you think I might be lying or you just like checking them. But as a reminder, for the normal exponential, if you have e to the x, a normal exponential, and then raise that to the nth power, you get e to the nx. And similarly, if you have a matrix exponential, e to the matrix A, and raise that to, let me call it the tth power, then you get e to the t times A, the exponential of the matrix, scalar t times matrix A. Similarly, matrices deal well with exponentials deal well with differentiation, don't they? If you remember, d by dx of e to the ax is you just bring the a out in front and you still have the e to the ax. And you can check that the same thing works with matrices. If you've got an e to the t a, you just bring the a in front. And of course, by what we said just above, just here, this is also equal to e to the t a, if you prefer to write it that way around, because a matrix commutes with its own exponential. But if we look at what we've just written here, let's go back to what we were saying about the forward and backward equations. So forward and backward equations were, the forward was that d by dt p of t equals p of t times q, and the backward was the same thing, was equal to q times p of t. But if we compare that to what we have in the red box, I think we can see that if we set p of t equals e to the qt, then when we differentiate it, we just get a q in front, or if we prefer, a q out the back, and those are the forward and backward equations. So in fact, this matrix exponential, p of t equals e to the qt, solves the forward and backward equations. I suppose we ought to, strictly speaking, we ought to check that it also satisfies the initial condition. P0 is e to the q times 0, which is e to the 0, which we said we were interpreting as I, and that is indeed the initial condition for the forward and backward equations. So this solves the forward and backward equations. And so in particular, that is the transition semigroup. P of t equals the probability of, the ijth entry of that is the probability of going from I to j in time t, because it solves the forward and backwards equations. I guess whilst we're here, we could also check the semigroup property. If you remember, that's that p of s plus t equals p of s p of t. So using that solution there, p of s plus t would be e to the q s plus t. But again, we can use our old friend, the properties of exponentials, to make that e to the sq plus st, which of course is e to the sq times, e to the t q, e to the tq, and that is p of s, p of t indeed. So we also have the semigroup property. So everything is just working out lovely when we use the matrix exponential. So I have in the notes just stated as a formal theorem kind of what we've learned in this section and the previous one. And it's this. Remember that we defined the transition semigroup to be that, which is that Pijt is the probability from going from I to j over a time t, perhaps with movements in between. And then we had the forward equation, which was that. We had the backward equation, which was the same thing, with the q and the p the other way round, as in the forward equation. And then we saw it was solved by the matrix exponential. So that's just like writing out in a theorem all the things we've done in this subsection and subsection 18.2 as well.